Well, welcome to this session coming to us from Hari Thantry at Google. Hari is a software engineer, and Hari is going to talk to us about P4 for NICs and giving us the perspective from Google's side as a cloud provider. This is a topic I'm really interested in because I think one of the biggest developments in P4 in the last year or two has been the fact that it's now making the jump from being mostly focused on switches to increasingly being used on things like DPUs and IPUs. And we've actually got a whole panel on that topic as well at this workshop. And so, we're starting to hear that P4 is not just for programmable switching, but for other forms of programmable infrastructure. So I'm really looking forward to this talk where we can hear from Google's perspective why they've adopted this new approach to having programmable infrastructure. And with that, I'll hand it over to Hari.
Hi, thanks, Bruce. My name's Hari. I work at Google in the host networking group, and we basically work on network endpoints, so that's NICs. As part of the effort at Google, we're starting to code our fast path data planes in P4. Before we get to that, let me give you a quick summary of Google's network. So Google infrastructure basically consists of many data centers that interconnect many racks of machines in a cross fabric design. So this allows us to have very quick low latency east-west traffic, and these data centers themselves are then connected together through our fabric networks, which interconnect either our data centers together or interconnect our data centers to the rest of internet. The core fabric network itself is SDN controlled, and we optimize for latency reduction and forwarding packets through our core networks. What this means is that we don't do complex packet transformations through this fabric. And we don't apply ACLs in our core fabric except for at the edge. Google Cloud actually shares this infrastructure with the rest of Google. So in Google Cloud, on the host, there are a few stacks that affect this packet transformation, since we don't do any packet transformation in our core of the network. So we have what we call a SNAP, which is an OS bypass user space packet processing framework that we use to build packet processing pipelines. It has taken many years, and it's somewhat equivalent to DPDK, but it's really a platform that allows us to construct packet processing pipelines on the end host. Andromeda is our cloud networking pipeline. So it's built on top of Snap, and it's the end host cloud stack that enables VM to VM communication, enables VM to communicate with Google services and the rest of internet. Andromeda performs the necessary encapsulation on a packet that leaves the VM so that the packet can find its way to other VMs and egress from the Google network. We also run congestion control stacks on top of Snap that enforce rate limiting and provide pathing alternatives to pick an egress point for our internet directed traffic. Snap coexists with Linux networking, and that drives a lot of native Google traffic. So in all, our end host packet processing and networking stack is fairly complex. It has many stacks, all of which need to collaborate together for us to have for us to provide fairness guarantees to all network flows as they egress the host. So in this scenario, if you notice, because we have a fairly complex network packet processing stack, these packet processing stacks take a lot of CPU cycles, and all CPU cycles that we give to network protocol processing or packet forwarding is a cycle less that's available to VMs that run on this x86 box. This translates actually to revenue loss, because the lesser number of VMs we can run on end hosts, because we have to spend these CPU cycles on forwarding packets, is lesser revenue that we realize. In addition, we have, because these packet processing stacks also take up host memory, that's also less memory available to the rest of VMs. And certain use cases like bare metal flows, which basically means that we can't run any OS or any of our stacks on the end host, means that we have to by necessity offload all our packet processing and all our Google specific software onto a third element. And this third element now becomes what we call as the DPU, the data processing unit. So the data processing unit is not only an economic there's not only an economic argument for DPUs. There's also it's also a necessary component in our network processing stack. So where does that lead P4 into? So given that we are a cloud vendor, we need to remain somewhat vendor agnostic. We need to have standardized mechanism to express the universe of packets that leaves our host. We need a mechanism to express transformations that happen on such packets as they leave the host, and we need a mechanism to that is somewhat mature in the networking industry. So P4 has been a declarative framework. It's a language and a framework that's being used extensively in the switch world express forwarding pipelines. So it's natural that adoption of P4 would be a good starting point. But there are some drawbacks and some shortcomings of P4, and that's the whole point of trying to improve P4 for NIC, which is that NICs are essentially an endpoint element, and routers or switches are basically transit elements. What that means is that for the endpoint elements, we also need a way to express things such as when a packet is transmitted, the host needs to know that the packet has been transmitted. The host needs to free buffers. The host needs to do, descriptors need to be posted back into the queues. So all of these features today are not expressible using P4, and that's what we want to see. This and some of the other things as well. So this this figure basically shows what I was briefly alluding to in the previous slide. That in essence, we have a machine. The machine may consist of a host. It may consist of multiple hosts. And on those hosts, we have VMs running inside those hosts. So if you notice, there is a concept of a queue pair. Where we have RxTX elements on the queue. We have and all the components that are P4 modeled. I've highlighted. So we can have notions of virtual ports. We can have notions of ports. We can express the vSwitch forwarding pipeline, and we can express that the fact that missed packets go to a control plane element, and we have mechanisms in P4 to express that. We have the P4 runtime that allows us to add, remove entries into tables in the vSwitch forwarding pipeline. So all of that is fairly good. What we lack is an ability to express completion events for instance, when we send these packets out into the fabric, we would like to post a completion event into a completion queue. We want so that the host can then free up the buffers. We want an ability to express certain endpoint offload blocks. We want, for instance, we want an ability to express things like TSO, LRO. We want an ability to. So how do we express these fixed function blocks? We want an ability to express encryption because we want to send encrypted packets on the wire. Today, we don't have a mechanism to do that in P4. So to summarize, we're looking at P4 for NIC, and we're asking for language extensions. So some of these language extensions that are being asked for is being actively worked in the PNA forum, which also includes a lot of other vendors. And the basic summary is in NICs, the principal way to express work to a pipeline is through descriptors. So what we'd like the community to think about is to have a standardized descriptor format, right, which becomes part of an architecture definition. That makes it useful to be adopted by a larger community. And this enables us to express features like TSO, LRO, RSS, encryption, decryption, uh, as metadata elements that are posted into this pipeline. We're also looking for machine model standardization. For instance, what is the size of metadata that could be made available to a P4 pipeline for offloads? What's the visibility of this metadata between the host and the device, between the device and the rest of the CPU complex that resides on the DPU? What is the host and device handshake mechanisms for, so this involves things like completion queues, etc. Plus, how do we express per viewport parse graph? So if you looked at the previous figure, we have, and Google use case, we have packets arriving from the host which need different treatment than packets that arrive from a VM. We want to have associate security contexts with with a VM. For instance, we don't want the VM to give the VM the ability to spoof as though it was sending packets from a host. So we need separate parse graphs. We need an ability to express that as part of the language. We need, so this requires some changes to the way we've thought of the P4 standard architecture for NICs. Like I've mentioned a few times before, we want an ability to express data plane events as a first-class language construct. We need a mechanism where we need to be able to notify the endpoint of packet transmission through completion events and other pipeline notifications. For instance, aging, which is also a feature in routers. We want an ability to say, oh, if we had an add on miss event where we missed a packet flow and the hardware automatically added the 3-tuple or the 5-tuple entry into a table, we want the control plane to be notified of such events. We want control plane to be notified if there is a counter overflow event or any network anomaly that we identify as part of processing pipeline for the packet processor. We want encryption as a core feature in PNA because encryption is extremely common in cloud providers, and it's the only way for us to, and it's almost a business requirement where we get keys from the customer and all the network traffic needs to be encrypted. Connection tracking, which is a feature that allows us to track TCP connections, to detect anomalies in TCP connections, and to reapply rules to a TCP connection when we re-encounter a SYN packet, for instance. Which is both hardware friendly and it's a feature that's available on most DPUs. We want an ability to express that as part of P4 language. Then for certain use cases, we would like an ability to say which entry across tables, which entries take higher priority, because a lot of architectures tend to use caches, and we want to guide cache replacement policy based upon entries that belong to a particular table. So in all, the laundry list of features that we would like to get from P4 is pretty large. And it's a very fertile ground, P4 for NIC. And greater industry and academia participation in extending this language for NIC use case model will drive faster adoption of both DPUs and P4 on NICs. So what do we seek? So essentially what we're looking for, and we're looking to collaborate with both industry partners, vendors, academicians on investments so that we can improve the ecosystem for running P4 and NIC programs. So today we have DPDK, BMV2 that are being extended for NIC, but we really don't have something that targets a DPU architecture. So we don't really have an ASIC software model. There are beginnings of that for certain hardware components like the parser, and extending that to a more abstract ASIC architecture that can then be easily lowered or can be improved upon by individual vendors would be a good starting point. So this would require investments into both a compiler targetable model and an open source IR backend for a software model that represents an ASIC pipeline better. Since P4 is declarative, it should be possible to automatically generate test packets through program analysis of the P4 program itself, for both for ex, both for parse graph coverage and for generation of table entries into the pipeline. We also would like to have a highly performant interface for programming of entries, because unlike the switch world in the NIC, convergence and entry insertion is a is a is one of the desirable targets for offloading to a NIC. So we'd like the industry to standardize around either P4 runtime or TDI, and the way we would pick one of these two would be based on both performance, tool chain support, and what is the ecosystem adopting? Is it P4 runtime or is it TDI? We'd like more long-term academia involvement in improving language expressibility, test generation frameworks, collaborations, and developing lower-level IRs for targeting the ASIC family architectures, which translates into a software model that is compiler targetable. So in all of these ecosystem investments would lead to better standardization in this space. It would improve our adoption strategy for DPUs because we can consume them faster, and it'll lower time to market for everybody involved. Thank you. So to summarize, I mean, I do believe that evolving the P4 language and its ecosystem to better express SmartNIC features remains hugely relevant to Google, and by extension to all cloud providers, because anybody who hosts VMs would want to offload it into a DPU-like architecture. So, and programming this DPU-like architecture for these many use cases of either NCAP, DCAP, or pathing through the network, or ACL support. All of these are features that P4 is good at, but P4 needs to be improved to sort of address the endpoint features that we talked about during this presentation. Thank you.
Hari, thanks very much. That was really, really interesting. I've got a couple of follow-up questions for you. First of all, that is definitely a long list of features that you're looking for with P4. It's really interesting to see how P4 obviously evolved as something focused on switches, and superficially, I think we look at something like, say, if you take the Mount Evans DPU, which I think your team was involved in, it's got this nice P4 programmable piece sitting in the middle of it. And so you kind of look at that and think, oh, it's going to be just the same as programming a switch. But clearly there's a lot of differences in doing what you need to do for a NIC or a DPU versus what you need for a switch. So do you think that P4, it doesn't have the right basic capabilities to get where you want to go? Do you think you're grafting all these features onto the right foundation, or is it the case that we should be looking at a different approach?
I think P4 is the right framework for expressing a vSwitch forwarding pipeline. So at the core of it, I think P4 has got it right. Where it's not adequate, and I must say where it needs to add on features, are these endpoint things that are not modeled at all. So the examples that I gave, for instance, how do we signal completions to the end host, or how do we generate event notifications from within the pipeline, or descriptor standardization, right? How do we describe work to this device? All of these, I think, are interesting problems to be looked at. I think PNA largely is looking at a lot of these things, but I wish we could get to the endpoint faster.
Yeah. Yeah, I mean, I think to me there's a really interesting kind of fundamental thing there, which is that when you think about a switch, it fundamentally operates on packets, and when you think about the NIC and the host, it fundamentally operates on descriptors of bigger things with complex metadata, and it's almost like we started from a particular model of what it was we were trying to program, and that was switches. and now we've got a unit of work that's different than the packet. And that, to me, feels like that's maybe the fundamental tension between trying to create programmable NICs versus trying to create programmable switches. Do you think that's a fair characterization?
Absolutely. I completely agree with that characterization. I also feel that the switch architectures are more regular. So they
Yeah.
also lend themselves better to there are more options in table placement in how a compiler views the switch architecture versus a NIC architecture which has a lot of specialized blocks. And we need
Yes.
to find a way to express these specialized blocks in people.
Yeah, I mean, it's. I think it's telling if you look at something like the block diagram of Mount Evans, right? There's this nice little regular piece that's the P4 bit, but there's a lot of other stuff in that chip, and as you say, it's a kind of different balance from a switch.
That's right. Yes.
Yeah. Um, I did want to get back to some of the more basic stuff in your talk too, which is this kind of argument that you need to move more functions into DPUs because they're taking away cycles from from the server. And I've heard this argument a few times, and one of the things that worries me about it is, so the work has still got to get done, right? You've got to do the work. You're saying, well, I had one option of doing the work on my x86, and now I've moved it onto a different piece of hardware to do the work somewhere else. I still have to do the work. So it's not exactly that the work becomes free, it's just that it's being done on different hardware. And so, has anybody actually done the sort of the costing to say, well, it's actually more cost effective to run, say, a vSwitch on a DPU versus just borrowing some cycles out of the x86?
So I think you're referring to the economic argument piece, and I believe it is the case that over the life. So I think there was some study done at Microsoft, which basically charted, and it was published to open to in a paper as well, which basically said that over the lifetime of a Xeon server, it earns about $5,000 based on all of VMs that it hosts during its entire lifetime, and the cost of a DPU is much lesser than that. So that's the economic argument part. What we're missing is that networking speeds are growing at a much faster pace than what the Xeon can comfortably handle. So we're actually allocating more and more and more budget to networking on Xeon hardware. Now, it might have been possible at 100 gig, but at 200 400 gigabits per second, you need you need a specialized forwarding engine to anyway forward packets or do transformations for packets through your pipeline. So that's it's not just the case, it's not just the economic case, it's also that Xeons simply can't keep up
Hmm.
with the packet rates that we're talking about.
Yeah, I mean, clearly the industry is going down this path, right? I think Amazon was quite early in deciding they were going to have dedicated hardware for doing these functions. As you say, it's yourselves, it's Azure. Everybody's going down this path. One of the things I'm wondering is, so that, like, I think the argument holds up when you're looking at people operating at the scale that Google does, and I don't know if you have an opinion about this, but do you think the same argument will hold when we go more down market? So if we go to, say a big enterprise data center, are we going to see the same argument in favor of moving these functions into DPUs or IPUs?
So it is very true for cloud providers for the scale of Google, but it may also be true for vendors like VMware, which might not be able to, which might have licensing restrictions on things like bare metal, right? So they cannot run their stack, they cannot run their control plane on the hypervisor, so they can't do these packet transformations on the hypervisor. So even for them, there is a need to use something like a DPU and offload their processing to the DPU. As far as enterprises go, I believe it will be driven by economics. So at the end of the day, the merchant market silicon, especially in the switch world, right? It quickly moves into a point where it becomes cheaper to buy uh, the current generation part than buy the previous generation part. So the economics of per port speeds that are being offered would force you to upgrade your switch infrastructure. Once you start upgrading your switch infrastructure, NICs follow. And if NICs follow, then, and if the hosts can't keep up, then DPUs will probably become ubiquitous. And in that sense, I believe, at that point, the price for DPUs also will drop. So
Yeah.
it is a very interesting transition, which is, I think the cloud vendors would probably be the first to adopt it simply because of business reasons, scale reasons. But it will come to a point where I believe enterprises also, it would make economic sense for them to adopt it as well.
Yeah. Yeah, and clearly, I mean, I think from my understanding, my former employer, VMware, seems to have that view too, right? That they've got their Project Monterey that's going down that path, and certainly your point about bare metal is a good one, which is like one of the nice things about having the network processing being done on a DPU is you no longer need to have a particular operating system running on the host to deliver those functions. And that was one of the use cases for Project Monterey that kind of caught my eye. So so it does seem like this is going to be a classic kind of trickle down into the enterprise sort of story. So I guess the other thing that kind of caught my attention was, you're asking for a lot of people to come and help. And clearly you need a community of people building tools and open source and so on. Do you think that community is developing? Like, are you optimistic that we'll get the right level of attention coming in and delivering the kind of tooling that you need to make this all succeed?
I hope so. We are seeing progress along. We're seeing progress along multiple fronts with with many vendors, and vendors are enthusiastic as well. But I do believe that the focus of P4 needs to be on NICs because they are the more interesting platform.
Yeah. Well, you would say that.
No, I do believe so. I think it has more challenging problems to solve, simply because around compiler placement, around what is the there are table placement, parse graph realizations, specialized processing. So there are a lot more. It's a more fertile ground. So I hope that that both academicians get interested simply because it's an interesting problem to work on, and vendors get interested because the whole cloud market is moving that way. So I do hope to see convergence build up over time, and that would be useful to the whole industry.
Yeah. Well, look, I think that's actually a pretty good note to finish on, and you won't find me arguing with you. I started working on NICs 30 years ago, so I fully believe they're an interesting problem space. But yeah, so I think that that's a great message to this community too, which is that, don't just think of P4 as the thing that does switching. It's the thing that's going to do a whole new class of infrastructure, and that there's a fertile ground there for people to jump into. So I think that's probably a good place to wrap it up for today and send that message out to the community. And Hari, I'll just say thanks very much for a really, really fascinating presentation.
Thank you, Bruce. Thank you for very insightful questions. Thank you.
All right.